Okay, let's move into the worksheet number 5 from the lecture number 5. In lecture number 5, we mainly discuss about the centripetal force, right? Centripetal force is another force that we need to discuss that can be calculated by using mass of the moving object and tangential velocity of the object divided by the radius that object will make circular. So now if I have object M moving with the circular path, if this object sitting on R distance and make the circular pattern, and if this object have a velocity V, that will be the centripetal force of that object. So we have centripetal acceleration, that will be V square over R. So that is the force towards the center. Now centripetal force will not be drawing on your free body diagram, because centripetal force will be another force that can be friction force, that can be tension force. Is depend on the situation, right? Because of that, we do not label the centripetal force as the force in free body diagram. Even your Newton's second law, net force equal mass time acceleration. If you write it to the center, toward the center of the circle, if you write this to the center of the circle, this centripetal force will never come in here, never be here, right? Centripetal force always in here, because it is coming with the acceleration part. Because of that, we do not draw the centripetal force on the free body diagram. Okay, so now second part of this lecture, we discuss about the gravitational force. If I have two objects, if these are sitting with the distance R, if this one M1 mass and M2 mass, there is a force in between these objects. That force, we call it as the gravitational, universal gravitational force. That will be the universal gravitational constant times mass of first object, mass of second object, and distance R squared. So now this force is acting in between any two objects. It can be astronomical planets, or it can be two people on the earth, right? It doesn't matter. This force is always there. But when we are working with the earth objects, we do not consider this force as a force, because that will be a very small force. We're going to see the calculation on the bottom why we do not take this force as a force in the free body diagram when you do it on the earth. But when you have the object exactly on the surface of the earth, this is my earth, if object sitting on here, then this object has the force of gravity downward direction. That force in that case will be equal to this G M1 M2, if this one is M1, right, divided by R square. In this case, R will be earth radius, right? So now in this case, you can see that we can get the connection of lowercase g and uppercase g, because this will be mass of the person M2, right? M2 times G is equal G. M1 is the mass of the earth, M2 is the person, and R is squared, and then M2 will cancel out, right? This is where that you will see the connection between lowercase g and the uppercase g. Uppercase G is this mass of the earth squared G value. Right, this also explain you when radius is greater, that means if you have somewhere here the object, then your G value is lower because your R is increasing, right? That will give you the information about the mountain area. Your value G is less than the value that we are using as 9.80. And also different places, and the you can have in north and south pole different G than the elevator, equator G value, because equator G value is different. The reason is when you are sitting on here, you are going around this circle, right? Because earth is keep spinning. Because of that, there is a centripetal force happening because of that. But if you are sitting here, you are spinning just around you. That means there is no centripetal force that will affect to the G value at the equator, different from the north and the south. So I discussed this everything on your lecture note. Please make sure that you watch those things. Okay, so now let's move into the question on the bottom and try to understand this little more: centripetal force and gravitational force. Okay, so now I'm going to do part A first. Okay, let's do part A first, right? And if a car is traveling on an unbanked curved road, I talked about the unbanked and the bank road. Unbanked means flat road, basically. Flat roads with keeping radius 10 meters and road, and the car has a static friction 0.5 coefficient, and draw the free body diagram and find the maximum speed that car can have without slipping, because car is going to take a turn, right? I'm going to draw it in flat, right? So we'll say I have a car here, right? So this is the road, right? So now car take the turns on the flat road, but this, we know that this object has force of gravity downward direction, and that will be m times g, and there is a normal force, right? So in addition to that, this object has the friction force in this direction, because this friction is not because of the friction on the tire on the road, right? It is to the center, because this object going to go this path. Because of that, there is a static friction between tires and the road towards the center. That is what the centripetal force in this case. Okay, so now radius of this is given. Let's take one, the significant point, one decimal place to make it significant correctly. And we have static friction coefficient 0.50. So now we have the free body diagram. So now we need to find what velocity we can have without slipping this the car, right? So now we're going to write Newton's second law towards the center. Net force equal mass time acceleration. We're going to write toward the center. In this case, it is my drawing, it is x direction. So now net force toward the center is friction force. Should be equal to mass time acceleration is a centripetal acceleration velocity divided by r, right? So now we know that friction force will be static friction times normal force will be equal to mass the square r, and I need to just find the v, but before that I'm going to plug the normal force in here. Mu s, normal force is equal to, if you write the Newton's second law in this direction, we have normal force minus force of gravity equals 0. Because of that, normal force equal also mg, right? So mg equal mv square r. M will cancel out. From this, I can write v equal mu s radius g and foot. Right? Then we can calculate the v value. So that will be 0.50 times 10 meters times 9.80 and root of that. That will give you the velocity, that is the tangential velocity of the path of the vehicle. So that I have 7 meters per second. So now next question, if the car is traveling on bank curved road with keeping radius 10 meters on the road, draw free body diagram, find the optimum angle of the road, maintain the speed of the car 10 meters per second without slipping. Then now we need to draw bank curve. Bank curve means the ramp that you usually take has a incline, right? So now let's say incline theta. So now we'll say this is the car. car is going to take a turn, but you know that your car is taking the turn with the radius here, not the radius in here. It's not taking the like this. What it does is it will do this kind of circle, right? So now we need to draw the free body diagram first, and we know that this one has force of gravity that will be m times g, and there is a normal force perpendicular to the surface, normal, and in addition to that, this object can have the friction, but I'm going to show you without friction in here, okay? Because we can take the turn on the bank road even without the friction, but on flat road, you see that you need the friction. You cannot do anything without the friction, right? That means flat road are more frictional than the bank road. Bank road, you can take the turns even without the friction, okay? I'm going to do without the friction in here, right? So those are the forces I have. Now let's draw your x-axis. Yeah. So now you can think why I draw the x and y here. I told you to draw the x and y earlier on the direction of the plane and the perpendicular, but here I'm going to choose my real x and y or the usual x and y, because I know it is useful in this case to find the angle theta easily, okay? So now other way also you can do it, okay? So now we're going to write the net force equal mass time acceleration towards y direction first, right? If you do it y direction, you see that now we need to get the trigonometry again. So now this angle is theta, and do you able to understand this angle is also theta? Okay, do the math. So you have this one is 90 minus theta, 90 minus theta, and this will be theta. According to that, I know that this angle also should be theta because this will be 180 degrees. Okay? So I understand it is theta. If you not, let me know. So now net force towards that is normal force times cosine of theta, right? And but my FG is in negative direction, equal, there is no acceleration in y direction. This car is not going to fly, right? There is no acceleration on that direction. So now from this, I will be able to write Fn cosine of theta is equal to Fg. I will write it as my first equation. And then I'm going to write net force equal mass time acceleration towards x direction. Now towards x direction, net force I have is, you see that normal force has the force towards the negative x direction, right? So that will be negative Fn sine of theta, right? Should be equal, there is no any other force, should be equal to the mv square over r, that acceleration, that is the centripetal acceleration, also to the left. Because of that, I have negative. Now negative will cancel out. I'm going to rewrite this as Fn sine of theta is equal mv square over r. So now 1 and 2 is there. I just need to find theta, right? So easy way to do it, I'm going to divide 2 by 1. That is your choice. You can do whatever way you need, but I need to find the theta value, right? So now if I do that, I have sine of theta divided by cosine of theta. Fn will cancel out. That will be equal to v square over r and g. Okay, because Fg is mg, m will cancel out. So now this will be, and another way, sine of theta divided by cosine of theta is tangent theta equal v square over rg. So now theta will be tangent inverse v square over rg. Since we have all the numbers, we will be able to find it. So tangent inverse V squared is 10 meters per second squared divided by R is 10 meters and G is 9.80, and this will give you the value of theta, optimum angle we call it as 45.5 degrees. So that is the standard way of solving that problem. Okay, so that's the easiest way to find the theta angle. Otherwise, you can write your x and y axis on the other direction and to do the problem in different way. But it is possible, but it will take little more steps than I did. Okay, so now let's move into the question number 2. So let me see what happening here. Okay, so now this question, actually, I am trying to explain you how the gravitational force is acting on the surface or outside the surface or on the surface in different objects, these kind of things, to understand how G is different, or the F is different for those calculations. So let's move into the part A first. So part A is taken, so you have G value given and mass of the earth is given and radius of the earth is given. And find the gravitational force on the person of 65 sitting on the earth. So now we have the, cannot compare the size of the man to the earth because earth is a big object, right? So we'll say mass of this person is M and mass of the earth is E, and this distance is RE, right? So now we know that there is a force on this person when he's sitting on the earth. That force will be this direction. That force will be able to calculate by using GMME over RE squared, right? So now if you calculate this one by using those informations, let's plug it in. 6.67 times 10 to the negative 11, and then times mass of the person is 65 kilograms, and times mass of the earth is 5.98 times 10 to the 24. Going to divide by radius of the earth and power 2, 6.38 times 10 to the 6 meters. Okay, so since everything is SI units on the meters, and then F value you're going to get as 637 newtons. Okay, so now quick check that you can do. Actually, when the person sitting on the earth, this F should be F of G, right? If you calculate the F of G by using mass and G, you also going to get around 637 Newton. That means when it is on the earth surface, that will be basically the same force. Force of gravity is equal to the force acting attraction between earth and the person. Okay, same force. Okay, now let's move to the part B. So now part B, what it's saying is find the gravitational force between this person and the tower with the mass of 2000 kilogram located 1000 meters away. So now these both objects are sitting on the earth. There is a tower, right? Distance between these two is the now R, and now mass of this M and mass of this M, right? So now we know that again gravitational force in between these two objects will be able to write by using G times mass of the person, mass of the tower, distance R squared, right? So now you have all the information. Plug it into here, what we'll see. 6.67 times 10 to the negative 11 times mass of the person 65, mass of the tower is 2000 kilograms. I'm going to divide that by the radius R is 1000 power 2. And now if you calculate the F in here, you will see the F I get is 8.67 times 10 to the negative 12 Newton. See that how small is that force is? That's the reason that we do not consider this force basically when you do the forces or Newton's second law on the earth, because this force is very small compared to the other forces we are talking. So now see. Now C is what? C, find the gravitational force. Find the gravitational force between Earth and Moon. Mass of the Moon is given. So now we have Earth and the Moon, right? So Earth and Moon and distance R, right? So now force will be equal to, again, G, mass of the Earth times mass of the Moon times divide by distance R squared, right? Again, plug the values. So now you will see when you go to the astronomical system or the planets, you're going to need this force because it is a greater value now, times mass of the Earth is 5.98 times 10 to the power 24, and mass of the Moon is 73522, 7.35 10 to the power 22, and divide by the distance now 3.84 times 10 to the power 8 and power 2. So now after you calculate this force, that will be closer to what I get is 7.63 times 10 to the power 20 newtons. You see that it's a now greater force when you consider the Moon and the Earth, right? So now part D, see part D. Explain why didn't consider this force between two objects on the Earth. Here we explain it. Because when you take the two objects on the Earth, force is smaller, right? Force in this case, negligible compared to other forces. Okay. So that will be part D. Okay, so now we're going to move into the telescope and calculate the speed of the telescope, right? So speed, determine the speed of the Hubble Space Telescope orbiting in the height 598 kilometers above the Earth's surface. So that means your Earth is here and telescope is here. That means this is the distance given. I'm going to write R1 and this will be R Earth, right? R1 is the one 598. 98 10 to the power 3 meters. Okay. And RE is given and we need to find the speed. So now before doing anything else, I need the R distance. R distance is because this telescope is going to move around the Earth with some speed. That's what we need to calculate. Now centripetal acceleration will happen on this circle. Because of that R, I need is R1 plus RE, right? Let's do that first. R1 plus RE, you have R1 is, I'm going to write by using, let's write it 0.98 times 10 to the 6. I can do it, right? I can bring the decimal place into 6. And because RE is 10 to the power 6, as you see, 6.38 times 10 to the power 6. Then after you add these two together, that will be 6. Add it, we have 8, could add it here, and then 8 and 9, 7, and 5 and 3, 8 and 9, okay, times 10 to the power 6 meters. Okay, so that is the R I need. Now I know that I can calculate the force by using G, mass of the telescope and mass of the Earth. These are the two objects now, and distance between these two objects are squared. So now, since this will be the centripetal force, right? So I will be able to write this as the centripetal force. That will be the mass which rotate at the telescope and velocity square over r. Okay. So now you can see telescope mass will cancel out. One of the r will cancel out. Then I can write the velocity as g m earth divided by r and root of that. Okay, let's plug that into here. G is 6.67 times 10 to the negative 11. Mass of the earth is 5.98 times 10 to the power 24. Going to divide by the r, we just calculated 6.978 times 10 to the power 6 and take the root. So now velocity of the telescope is 7.56 times 10 to the power 3 meters per second. Okay, so we're going to move into the last question. So this question will be a roller coaster question. So this question, actually in here, I am talking about without the friction and without the energy conservations, and I did not talk about any of those yet, but I want to emphasize that this question we're going to solve by using energy conservation and by using rotational motion and by using frictional informations throughout the semester. This reflect back again and again throughout the lectures. Okay, but here is very simple. It's just going to study it by using centripetal information to find the minimum speed must it have to at the top of the loop in the order to remain in the contact with the loop, right? So now, and the roller coaster is mass 20 kilogram, right? So that is what going to do the centripetal motion, 20 kilograms. And the radius is 5 meters. So what the minimum speed? That means when this object go around this one, this will go on the top and then it will fall down back into the track again on the bottom, right? So now what the question is asking, what minimum speed must it have at the top to take this turn, right? So it's very important. At top we have basically normal force, right? So normal force in that case, you see that here, right? You have normal force downward direction and also force of gravity downward direction, right? So now if I write without considering anything in happening here, if I write towards the center in downward direction, net force equal mass time acceleration, what happen is you have force of G, you have also normal force that will be equal to the mass time acceleration, in this case mass velocity square over r, right? So now the important information is I need to keep this on the track. That means I should not fall down. What I should have is normal force at that place should be equal to 0 to have minimum speed. You understand what I'm saying? So if n equals 0, that you can have minimum speed. But if n is there, then I have a larger speed than that. I need to make this to 0 to find the minimum speed. In that case, velocity will be minimum. Okay, so now Fg equal mg is equal mv minimum squared over r. M will cancel out. So now we can find the minimum speed as gr and root of that. Okay. So now you can plug that value 9.80 times the 5 and root, that will give you minimum speed as around 7 meters per second. Okay, so that's it for this chapter, this lecture.